Sass class with Amanda. Hey. Hello, in this video we'll cover least squares regression. Our learning objectives are 1. To state the purpose of the least squares method, and 2. To motivate the formula for the least squares regression line. Let's just remember an example from many videos ago where we studied the relationship between the weight of an object and the force with which it hits the ground. And here's the graph from that video, okay, where weight is on the x-axis and force is on the y-axis. Okay, so what is a regression line? A regression line is a straight line used to predict the outcome, or the y values, given a value of x. So a regression line is a straight line used to predict a y value, or a response or an outcome, given a value of x. Okay, so let's just remember what we know about lines. Well, we know that the equation for a line, which we learned in algebra, is y equals mx plus b. Okay, where x is our input and y is our output, and we know that m is our slope and b is the y-intercept, or the vertical axis intercept. I want to be more general because x and y are not really the names of these lines, they just happen to be the most common names for these lines. Alright, so we know that the equation for the line is y equals mx plus b, but what is y equals mx plus b? It's a straight line. And what did we see in our videos when we were describing form for the relationship between two variables? Well, we know that a straight line will never pass through every point. Okay, so if you need a visual, just here's a graph, here's a bunch of lines. This time I'll draw one with a negative association, or I guess these are points, my bad. Alright, and so if we drew a straight line that follows this pattern, right, so here's our line, not as straight as it should be, but straight enough, and we see that this line doesn't go through this point and that point and that point and that point, because what we actually need for that to happen would be some sort of polynomial, okay, or some other curve. Okay, so this is not possible. So why are we talking about straight lines? So the goal is to find a line that minimizes the distance between the points and the line itself, okay? So the goal is to find a line that minimizes the distance between the points and itself. So to think about this visually, let's say that this is our line, okay? So for the vertical distance, imagine this line here, right? This line, and there's another vertical line here, and there's another vertical line here that we can't really see. These 2 points look like they're on the line, so we won't draw vertical lines because their height is 0. So we see that this line might be minimizing these distances, right? We want these distances for every single point at the same time. We want these distances minimized, or as small as possible. And so the method that we're describing when we're talking about the vertical distances is the least squares method. Okay. All right, so let's just write that out. This method minimizes the vertical distance. Again, it's important to specify this because there are several other methods. And what does it produce? This method produces what is called the least squares line.
And this least squares line involves the sum of squares.
So to understand this a little bit more, for each xi, or each explanatory value, there is a response value and a value that the line gives us, okay? And that difference is yi minus y hat I, okay? And what we want to examine is the total difference. So what is that? That means for y1 minus y1 hat squared. Okay, these are the vertical differences. So I'm just going to draw a graph here on the side just so that you can see what I'm talking about, okay? So here's our least squares line. Here are some points that are sitting around this line. And here are our vertical distances, okay? But remember that each point on a Cartesian plane can be notated as x1, y1, okay? And so maybe this point is x2, y2, and this point is x3, y3, and this point is x4, y4. Oops. Okay. So we're looking at these points and what's happening at this line, okay? And what is that point? Well, that point has the same x value, right? But it's the y value that's different because it's further up. So what we're just going to make these two y's different and call this y3 and call this y hat 3. This is a little hat, so think of it as a y in disguise. Here, same x value, so let that be x1, and so then this is y hat 1, okay? This point, this is same x2, but now we are dealing with y hat 2, okay? These are the values that the line gives us. So each of these differences, okay, this difference right here is only looking at the difference between the y's because the x's are the same. All right, and so what we have, if you think about it, the distance between these 2 points, so let's just think about it using our algebra that we know. What was the formula for the distance? Well, it was whatever your x values are, x3 minus x3 squared, plus then the difference between your y's, y3 minus y3 hat squared, with a square root, right? But This is just 0, so we can cross that out. And what do we have? We have exactly what this squared difference is that we're talking about. Okay, so what we're actually looking at is the square of the distance for all of these points at the same time. Okay, so it's y1 minus y1 hat squared plus y2 minus y2 hat squared, and let's just say we have n data points. And in the case of this example, there's 4. And so this is our equation. Okay, and if we were to write this in summation notation, okay, remember we do use sums. We have our sum over I equals 1 to n, because there are n data points. And this would use this general term, or this general difference here, yi minus y hat I squared. So since all the values on the line we're using y hat, let's just go ahead and change y equals mx plus b to be y hat equals mx plus b. So we have a bit of consistency in our notation. And what is m equal to in statistics? Well, our slope is equal to the correlation times sy, which is the standard deviation of the response variable, divided by sx, which is the standard deviation of the x variable or explanatory variable. Okay, and you can sort of think of this as the change in y over the change in x, right? Because the standard deviation represents variability. Okay, so this sort of is an intuitive formula. And I guess I'll write out that this is the standard deviation for the response variable, just so you have that in your notes. And this is the standard deviation for explanatory variable. Okay. And then our b, what is the y-intercept, or the vertical axis intercept? That's equal to the mean of our response variable minus the m that we just found times the mean for the explanatory variable. Okay, so remember that these are means. Mean for response and mean for explanatory. All right. So if we put this together, then the equation for our linear regression line using the least squares method is y hat is equal to r sy over sx. Okay, and again, think of this as the change in y over the change in x, and that's m times x plus whatever b is, and we said that that is y bar minus m times x bar. So I would recommend finding m first, just because you need it to find b. So first find m, then find b. You don't have to have this formula completely memorized, okay, but you should be able to find sy and sx and y bar and x bar. So in summary, we talked about what the least squares method is, how it works, and what is the formula for the least squares line.